This is probably a good a place to distinguish between what's known as coherent light sources and incoherent light sources. And we've seen in the context of this two-beam interference, the intensity behaves like this, where this is, for the general case, is I1 and I2 are different, and then the phase difference is here. Now, usually, these light sources that you have may have many different wavelengths in it. Remember, ultimately, the light is produced with atomic energy level transitions that emit photons, and the time at which they emit and the phases at which they emit are generally all different, because they're emitting many hundreds of thousands of millions of transitions to get a bright light source, even of the same frequency. So you have to distinguish a couple of situations in which phi2 and phi1 are both constants for every transition that occurs here, and those would be coherent. These would be coherent waves. So in that case, if phi1 and phi2 are both constant from both light sources, doesn't matter what the constant is, but they do have to be constant. Then it's said that the waves are coherent, and that's a more unusual case. Well, in the old days was an unusual case and very difficult to produce. But nowadays it's pretty easy because a laser beam produces coherent light that all of the transitions are occurring in a stimulated emission that produces the same phase factor. And so unusual case, the case of coherent back a few hundred years ago, even 100 years ago, very difficult to produce. And the more common in those days especially was the case where they depended on the time of the transition, etc., that each individual atom occurred. Of course, they didn't know that. So this delta, if you look at that, it's got this expression. These parts, K, the wavelength is, I'm assuming, is the same, the distances, so that never changes. So this delta, which is these sums, I can write as the cosine of the first term times the cosine of the second minus the sine of the first term times the sine of the second, where now these phi2 and phi1 are time dependent. And so we need to time average over those because they vary with the time. And what generally is done is they take 1 over t and average over all of them over one period of the wave to get the time average value of this cosine function and sine function. And so one has the time average value of the cosine function as the function times and the sine functions. And since these are randomly oriented, they're as often negative as positive, and so they both will go out. So on the time average, this term goes out for what's called incoherent light, that they're coming out with all different random phases at different times. And so the intensity is pretty much the way that you generally feel about it for incoherent light or incoherent waves. The intensity is just the intensity of the first one plus the intensity of the second one. I'd say that's pretty much everyday common experience. If you want, you got a light bulb, and you want the room to be twice as bright as it is with just one light bulb, we add another light bulb of the same sort, and you get twice the intensity from it. So